Check it out now, y'all.
NanoHub U, online instruction.
Hi, again. Welcome back. This week we're starting a new sequence of lectures in the course. We're essentially finished with the hydrogen atom and the quantum numbers and the quantum states that we've basically discussed for the last 2 or 3 weeks. And we're starting to move into that part of the course which discusses the quantum mechanics of many particles, okay? And the particles are governed, each particle is governed by Schrödinger's equation, but now what we're trying to do is collectively describe the behavior of an entire system. So it's a different emphasis than the previous lectures, and it relies heavily on concepts in probability. So this first lecture is just a general introduction to some of these concepts. Hopefully you've heard many of these words before, and you've had a course or at least a few topics or a few lectures in mathematics to introduce you to these probability concepts. But if you haven't, by the end of this lecture, you should understand the basic features that we're going to use for, let's say, the next few weeks in the course. So I guess the main message is that a lot of these equations that we've discussed in the past are not going to be used so much anymore. So Newton's laws of motions, the formulas for electrostatic electric fields, Schrödinger's equation, right? Those topics we're finished with essentially, and we're going to put a new emphasis on thermodynamics for the next few weeks of the course. So this course, as I've said more than once, tends to be a spiral, right? We keep coming back to the same topic, and we talk about it in a slightly different way. And each time we talk about it, we embellish it a little bit. We add a few extra features to the discussion. And the hope is that after you've heard these discussions 2 or 3 times, the basic ideas start to click, and you start to develop an understanding for the subject rather than just a rote memorization of a few formulas. So that's basically the goal of these next few lectures, is to give you the background and the information required for you to understand these statistical physics concepts rather than just memorize a whole bunch of equations. So we're going to discuss a number of problems in detail as we did for the hydrogen atom, right? We're not going to sacrifice the attention to detail in order to emphasize the main points. So it's going to be an interesting few weeks, and hopefully it'll be a new subject matter that maybe you haven't heard of before. So the big picture, I think it's always useful to try to give an overview of what we're trying to accomplish. And I think based on what we've already discussed in the course, it's pretty clear to all of you that the way one atom works is complicated, but it's by and large predictable once quantum mechanics is understood. So once you understand the formalism of quantum mechanics, you can understand how electrons and atoms behave. The trouble is when you start to put collections of these atoms together to form large systems, turns out the behavior is quite different, and it's non-intuitive in many cases, right? And so what we're trying to do is we're trying to develop a mathematics or a formalism or a way of thinking about these collections of big particles, or collections of many particles, right? And what we try to do is we try to capture some of the fundamental features that these big systems possess. And one of the important features is that there's, when you group together millions of atoms, right, there's a tendency for energy to disperse, to equally distribute among all those different atoms, right? And this dispersal of energy is actually accompanied by a loss of quality in the way that energy is stored. So that's kind of surprising. It turns out that there are different qualities of energy, and every time we use energy, we tend to degrade the quality of that energy, and that's a reoccurring theme throughout the late 1800s into the 1900s. So this loss of quality is something that was not anticipated back, let's say, in 1850. Okay, these spontaneous processes that we will discuss, right? They all seem to exhibit this spreading of energy. And this spreading of energy, what are the rules that govern how energy is dispersed in a system? Well, it's actually quite random. There appear to be no simple way to understand this. It just seems to be a chance occurrence or a chance collision of two atoms that cause the energy to be transferred one to another. And there's no way you can regulate these chance occurrences or these chance interactions when you've got millions of particles, right? It's just a random process. So the one way to track the quality of energy in a system, became a big issue, and finally in the 1860s, this concept of entropy was invented. We're not going to talk so much about entropy except towards the end of this set of lectures, but it's a very powerful concept, and it permeates all of thermodynamics. And I think the bottom line from this discussion is that this idea of chaos and randomness really become the drivers in these microscopic world of many atoms. The processes occur at random, and what we need are mathematics and concepts that are capable of describing that randomness. So it's useful to try to identify the generic problem we want to solve. And as always, this problem has different aspects, so we have to discuss different aspects of this problem. But in a very global sense, right? We're going to ask what happens when you take a large collection of atoms or electrons or molecules, you combine them into a system, and you hold that system at some temperature T. So you allow the system to come to some thermal equilibrium. And what we like to be able to do is we like to be able to come up with some microscopic understanding of this temperature T that the system settles down into. And in particular, we like to ask the question, how many particles in this system have an energy E as a function of the temperature T, right? So if we specify an energy interval or an energy increment dE, we want to know the number of particles within that energy increment dE that have an energy E. And that quantity is going to be called N of E and T. It's a function of energy and temperature. And it turns out that concept, that single concept, provides the key to unlock a huge number of problems that deal with many particles, many atoms, with collections of many atoms. So that's going to be a key focus for the lectures that will occur in the next couple weeks. I suppose it's useful to tell you what the answer is, right? And just maybe as a useful guide to where we're going. But eventually what we're going to show is we're going to show that this quantity N of E, which is a function of energy and temperature, right? This quantity specifies the number of occupied or filled states at some temperature T as a function of energy E, right? That quantity is going to be related to another function, G of E, which is known as the density of states. This basically tells you the number of quantum states available as a function of energy. And this quantity G of E is going to depend on the details, the individual, the specific details of any system that you're interested in. And the second feature that determines the occupied or filled states is this function f of E of t. And this function f of E of t is going to describe the probability of finding a particle in a given energy state E. And this function f of E and t is going to depend on temperature, as we'll show. And so the ability to distinguish between classical and quantum particles in this discussion is often relegated to this occupation probability f of E. So ultimately, at the end of this 2 or 3 week discussion, we hope that you have an understanding of this equation. It's a simple enough equation that you can memorize it, but what we're trying to do, of course, is we're trying to provide some understanding of how that equation comes about, and we want you to understand how you could calculate these different functions in order to calculate the occupied or filled states at some temperature T and some energy E. So that's the goal, is to provide understanding of this final result. Now, if you ask experts around campus about the way to achieve this understanding of this important equation, most people will tell you, at least most of the scientists will tell you, that you have to rely heavily on concepts from probability theory. And it's kind of useful to discuss up front why this is true. And I think if you ask 10 people, you'll probably get 10 different answers for why concepts of probability theory are so useful for discussing the collection of large numbers of particles. One obvious answer is that whenever you've got a large number of particles n, the only way to make progress is to start to use probability theory. Others might say that you use probability theory because it hides the incomplete knowledge we have of the behavior of each individual particle in this collection of n particles, right? But, to my way of thinking, what we're going to try to convey to you is how these macroscale thermodynamic principles, these 3 laws of thermodynamics that have been developed back in the early 1800s, how these ideas actually arise naturally from mathematical statistical laws that are applied to the macroscopic behavior of the particles in these quantum systems. So the system does not necessarily have to be quantum. It could be a classical system. If it's a classical system, then we're talking about an ideal gas. But when we start to deal with electrons grouped together in solids, then we have to rely on quantum mechanics to get the answer correct. So there are many reasons to justify the concepts of probability theory in this discussion. I think you'll get different answers from different people. But to me, the really key idea that comes out of this discussion is that these statistical laws, combined with the mechanics of a system, actually give rise to these macroscale thermodynamic laws that were derived before atoms were even understood, right? Before it was generally realized that atoms were real. So, to begin with, a few key ideas, right? What is a probability? Well, a probability is a number. It's a pure number, and it's devised to describe incomplete knowledge of a system. There are different distribution functions or probability distributions that actually describe collections of probabilities, and we're going to talk about distribution functions for the ideal gas in next week's set of lectures. There's a concept of multiplicity associated with this discussion of probabilities, right? So we say that if one event can occur in many different ways, let's say it can occur in n sub a different ways, right? So this one event A, whatever that event is, if it can occur in n sub a different ways, then we say that the number of possible outcomes of A is just the multiplicity, and the multiplicity is often given the symbol capital W, which means weight. It's often given the symbol small sub g, right? And we'll use these symbols to discuss possible outcomes of different events. And we'll illustrate some very simple events in this lecture and identify the multiplicities associated with them. The probability that a particular outcome results really depends on the number of possible ways that outcome can occur. So we'll try to illustrate that in a very simple way, and we'll have about 2 or 3 examples at the end of this lecture to calculate probabilities for very simple systems. And what we're hoping, of course, is we're hoping to build some intuition and understanding by discussing a number of simple, well-defined problems involving statistics, with the goal that you can use this intuition to better understand the physical problems that we're going to talk about in the coming weeks. So a few simple intuitive definitions. We like to talk about mutually exclusive and mutually independent events. So if I have a regular die, right, and if I roll that die, what we say is that the outcome is mutually exclusive because only one number can appear up after a given roll. So if I take the die and I roll it, right, and it comes up, in this case it came up a 5, right, we say that 5 is mutually exclusive to all the other possible outcomes because only one number can come up after a given roll. The other concept is this mutually independent concept, which means that the number that appears up after a single roll of a die is independent of the number up on the next roll. So if I did hundreds and hundreds of experiments where I sequentially rolled the die and recorded the number that came up after each roll, what I would find that there should be no correlation between the number that comes up on roll number 15 compared to the number that comes up on roll number 16, right? Each event is mutually independent if the die is an honest die. The other idea is the idea of possible outcomes, and I like to illustrate that by just saying that if I have 3 buckets of paint and I have 2 pieces of wood, right, and I can use any bucket of paint to paint any piece of wood, then it's important for me to be able to identify the possible outcomes of this very simple process. So since I can choose any bucket of paint and I can choose any piece of wood, there's going to be 6 possible outcomes of this experiment where I paint these pieces of wood with these buckets of paint, right? And it's important for you to be able to come up and be able to identify possible outcomes of an event once the event is described in a clear and sensible way. So that's another concept that we're going to use continually throughout the next few weeks of lectures. To illustrate this idea about multiplicity or weight, or sometimes it's called degeneracy, I'd just like to ask you to think about pulling, let's say, marbles out of a box, right? And let's say the box contains red and blue marbles. That's all they have. Let's say I decide to pull out 4 marbles from the box, I can ask, how many different ways can I get 4 red marbles in 4 sequential pulls of marbles from the box? And the answer is there's only one way to achieve that outcome, so the multiplicity of that particular outcome is 1. And the reason there's only one way to achieve it is because the first marble I pull out has to be red, second marble I pull out has to be red, the third marble has to be red, and the fourth marble has to be red. There's only one way that outcome can be obtained. On the other hand, if I ask what are the possible outcomes of pulling 4 marbles out of the hat such that 3 are red and 1 is blue, well, now there's different ways I can achieve that outcome, right? And in fact, there are 4 different ways, as I've illustrated in this slide. So the multiplicity or the weight of this particular outcome, 1 blue and 3 red, that multiplicity is 4. So there's 4 times more ways to achieve this than there is to achieve that, right? So another concept, another system that we're going to use to illustrate probabilities is just a standard deck of playing cards. I'm assuming most of you are familiar with these standard playing cards, right? Turns out there are 4 suits. There are red diamonds, there are black spades, there are black clubs, and then there are red hearts. In each suit, there's 13 cards per suit, right? So you eventually end up with a deck of 52 cards. And if you shuffle that deck, right, if you shuffle that deck to randomize it, right, the sequence of these 52 cards are completely at random. And so that's going to be an interesting question that we're going to use to discuss a few simple problems in this lecture. There are 2 theorems in probability that we like to mention, right? There's this theorem of total probabilities, and we say that the probability that an event C occurs is when event C is defined as either event A or event B, right? The probability that event C occurs turns out to be the probability that event A occurs plus the probability that event B occurs. So the key word in this is or, right? If you ever hear a probability problem and you hear the word or in the statement of the problem, then you're probably, you should immediately think of this theorem of total probabilities, and that just basically is telling you that you have to add the probabilities of the 2 events. So for instance, if you have a deck of cards and you pull one card from that deck, it's a fair question to ask, what is the probability that that one card will either be a 3 or a queen, right? Well, since there are 52 cards in the deck, right? Since there are 52 cards in the deck, right? And there are 2, and we're not specifying the suit of the 3 or the suit of the queen. So there's 4 3s, there's 4 queens, right? So the probability of pulling a 3 card out is 4 out of 52, which is equal to 1 over 13. The probability of drawing a queen card out, any suit, is also 4 out of 52, which is 1 over 13. So the probability of drawing either a 3 or a queen, with the emphasis on the word or, is just the sum of those 2 probabilities. And so there's about a 15% chance that you would pull out either a 3 or a queen. Now that system, that scenario should be contrasted to the theorem of joint probabilities. The theorem of joint probability says that if you define an event C as either or as the simultaneous, it's actually a simultaneous occurrence of event A and another event B, right? Then the probability that C occurs is the probability of A times the probability of B. And so the key word here is and, right? Whenever you hear and in a probability statement or a probability problem, that usually means you multiply probabilities together. So for example, if you have 2 decks of cards, right, and you ask what is the probability of drawing a red queen from deck 1 and a red queen from deck 2, so clearly and is shows up in the statement of the problem. Then you have to ask what's the probability of drawing a red queen from the first pack. Well, there's 2 red queens. It's either a diamond or a heart, so the probability is 2 out of 52. The probability of drawing a red queen from the second pack is the same. It's 2 out of 52. So the probability of drawing a red queen from deck 1 and a red queen from deck 2 is just the multiplication of those two independent probabilities. So the probability turns out to be 1 in 676 tries. So in principle, to achieve that outcome, you would have to do the experiment something like 670 times, and one time on average, you would achieve that outcome. So it's important for you to understand the difference between the joint probabilities in this case and the total probabilities in that case. The key words are or here and in the joint probability statement. Okay? So that's the theorem of joint probabilities. What I'm going to do in the next lecture is I'm going to work through some simple examples in detail to try to flesh out some of these ideas. So we'll be putting in some specific examples. So please come back and listen to that, because these examples might possibly help you understand some of these concepts that we've discussed here. So see you in that lecture.